The following is a special lecture titled The Death of the Dinosaurs. The lecturer is Stuart Sutherland, Senior Instructor of Paleontology at the University of British Columbia. Professor Sutherland earned his Bachelor of Science in Geology from the University of Plymouth and his Ph.D. in Geological Sciences from the University of Leicester. Professor Sutherland has been the recipient of several awards for his excellence in the classroom. Most notably, he is a two-time winner of the Earth and Ocean Science Teaching Award. Professor Sutherland also received the prestigious Killam Teaching Prize in 2006.
Hello, my name is Dr. Stuart Sutherland and I teach geology and paleontology at the University of British Columbia in Canada. Now, as you can probably tell from my accent, I'm not from around here. I grew up in the United Kingdom. I remember as a child being fascinated by all the bugs and critters I could find in the backyard, mostly because I could take them inside and scare my sister. I became fascinated by the diversity of life on our planet, by the species and their infinite complexity, even at an early age. This was compounded when I got older and my parents took me for walks in the hills around Derbyshire. Those hills in Derbyshire are composed of limestone, and those limestone hills contain some exquisite fossils. That's where I got the understanding that the biosphere isn't just a process that occurs today at the present, it has depth. It has depth in time. And it's that history of the biosphere that has fascinated me all the way through my career so far. And it's partly some of the aspects of the history of that biosphere that I want to deal with today. And in particular, I want to deal with times when that biosphere has gone into crisis. Those are what we call extinction events. So why is it important to consider extinction events? Well, if we consider that the Earth's biodiversity, our biosphere, is our Earth's greatest resource, and it is. It provides us with food, with medicine. It also regulates temperature and climate to a great degree. So it's important that we understand when and how that biosphere has gone into crisis, because who knows, we might be having to rely on that even more and more into the future. But it's difficult to get an understanding of that biosphere in terms of a long-scale process. We humans live for how long? About 70 years at most. That's nothing compared to the history of the Earth. So we need sciences like geology and paleontology to provide context for changes that might be happening to the biosphere right now. That context is vital, and that's one of the reasons why I like to study extinction events. So through this talk, I'd like to give you a brief outline of what the biosphere is in terms of how it might have changed over geological time. I'd like to also look at what an extinction event is. How do we define it? And how many has the Earth potentially experienced given the criteria that we define? And then I'm going to take one example, the Cretaceous Tertiary extinction event. That's the most recent extinction event that we've had on our planet in terms of a mass extinction event, and look at it in some detail. I'm going to pull out one thread though, and that is the possibility that this extinction event might have suffered from an impact from outer space, and therefore also investigate the environmental impact that that impact event might have had. Plus, let's have a consider as well as whether or not there could have been other factors involved in this particular extinction event. Is impact from space the only reasonable explanation? So, the biosphere in geological time. What is the biosphere? Well, it's the vast interconnected mass of all life on the planet and how it interacts with the atmosphere, the hydrosphere, and the very rock of the Earth itself. But the biosphere has evolved over time. It's not stayed constant. And we can see in this particular picture here a biosphere that comes from the Ordovician period. This is about 450 million years ago. And you can see it's a richly diverse, complicated biosphere. Right in the middle of the picture there is an orthoconic nautiloid. He's related to squid and octopus that we find today. He's snacking on a trilobite. That's an arthropod. You're probably familiar with some of those in fossil rock shops. But the rest of it might be pretty unfamiliar. It's a strange scene, an alien scene that we're looking at, but it is still complex and diverse in its nature. If we fast forward now in time, we're now in the Cretaceous. We're just 130 million years before the present. Geologically speaking, just a blink away. And things are looking a little more familiar. You can see here we have fish. There are turtles. There's even a flightless bird in there. But there are still components that are unfamiliar. One of the major ones being that creature right in the middle of the shot here. That's a mosasaur. That's the top predator in the Cretaceous oceans. My main point here is that the biosphere has evolved. It's a change through time, and it's changed its composition through time. It hasn't remained static. It's also true to say as well that the biosphere hasn't been experiencing continual complexity and adding new species to an overcrowded Earth. There has been times when that biosphere has been seriously cut back. So what is a mass extinction event? Because that's what we mean by cutting back the species in a pronounced and sudden way. And how many of those extinction events has the Earth experienced? That's going to be vital if we're going to understand current changes. It's important here that we understand a major difference between extinction and between mass extinction events. We can see the dodo here. Now, the dodo went into extinction. It's tragic for the dodo, but it's not really unusual for life. Extinction is the expected fate of any species. In fact, the maximum average time you'd expect a species to live on our planet is about 3 million years. When we have a mass extinction event, though, we're looking at a large number of species going into extinction all at the same time, at least 30%. 30%, that's a third of the biosphere that we're talking about here. That is a large number of species being removed from the planet. In addition, we need to see that that extinction event, if we are to classify it as such, occurs in a broad range of ecologies, in a broad range of ecosystems. So it couldn't just be in coral reefs. It couldn't just be in tropical rainforests, as tragic as that might be. It has to be, if we were looking at this particular image, in the oceans with the ichthyosaurs and on the land as well with the dinosaurs, across as many ecosystems as possible. In addition, and probably the most critical factor that we need to classify a mass extinction event, it needs to be short and it needs to be sudden. But remember that here we're talking geological timescales. And when we're dealing with 4.5 billion years of geological history, short and sudden means between 10,000 years to perhaps a maximum of 1 million years, which is just a heartbeat, blink of an eye geologically. So when we look at mass extinction events, how many can we recognise? Well, I'm just going to deal here with about the past 540 million years. It's a period that we call the Phanerozoic, and it's where life is most abundant and most diverse. And when we look at this period, we can find at least 5 major mass extinction events. We have one in the late Ordovician. That's the first one that we define in this particular period. Then we have one in the Devonian. Now, in the Devonian, that's probably a series of pulses of mass extinction events. But then the one that is most interesting to people who study biodiversity probably is that middle one there, the Permo-Triassic extinction event. I often tell my students that if nothing else shocks them in my course, apart from their eventual grades, is the amount of creatures that go extinct into this particular extinction event. In the Permian to the Triassic, we're looking at losing maybe 98% of species of the planet. Think of it another way, just 2% of species limp from the Permian and make it into the Triassic to repopulate the planet. That's pretty scary numbers. After we had the Permo-Triassic decimation, we are all right for a little while until we get to the end of the Triassic, where we have another extinction event, and then at the end of the Cretaceous, the most recent one, the one that we're going to be dealing with today, the Cretaceous Tertiary extinction event, also commonly called the KT extinction event. So, what are the characteristics of the KT extinction event? Well, the Cretaceous Tertiary extinction event is probably the most well known. It's the one that you see most often on television, for example, or in books. And that's because of one major factor. It's where we lose the dinosaurs, and everybody likes to hear about dinosaurs. It is definitely the dinosaur killer, but it's important to remember that it's not just dinosaurs that are suffering extinction in this extinction event. We're looking at losing over 50% of all species on our planet. That's 50% of the biosphere being removed. On land, if you're over about 25 kilograms, you're not going to make it. You're not going to survive. There are some notable exceptions. Alligators and crocodiles are going to make it through this extinction event. But in general, if you're big, you're in big trouble. Now, we've already said that if we have a mass extinction event, it can't just be on the land. It has to be in the oceans as well. And when we look at the extinction event from the Cretaceous, we find that the oceans really do suffer as well. We're looking at around about 80 to 90% of marine species being lost in the oceans. That's almost all of the species in the oceans going into extinction. That's fairly frightening. So we're going to lose these beautiful ammonites that we can see here, and these fantastic marine reptiles. Also, critically, we're going to lose a lot of marine plankton at this time as well. Marine plankton being the base a lot of food systems and food chains and webs upon which the rest of life balances. So what I'd like to consider now is one aspect of that extinction event. Because you see, the extinction event of the Cretaceous and Tertiary is really old news scientifically. We've known about it for really quite a long time. In fact, the early geologists noted that there was what you might call a faunal and floral turnover at that time. A lot of creatures went into extinction at the end of the Cretaceous, and new forms were found in the Tertiary. It was so pronounced, in fact, that they decided to create a whole new classification of geological periods. And the KT boundary marks the boundary between the Mesozoic, which is one group of periods, and above it, the Cenozoic, as a whole new grouping of geological periods. What is new news, relatively speaking, about this comes from a paper that was released in 1980 from a father and son team. This is Luis and Walter Alvarez. Now, Walter Alvarez is a geologist, and he was particularly interested in a clay layer that he found in a small and very beautiful town called Gubbio in Italy. What, you might ask, is interesting about a clay layer? Well, the clay layer there in Gubbio marks the boundary between the Cretaceous and the Tertiary. In effect, the clay layer is the extinction event. This fascinated Walter, and took a sample of that clay layer to his father, Luis Alvarez. Now, Luis Alvarez isn't a geologist. He's a very famous physicist, in fact, a Nobel laureate. So Walter took this clay sample to Luis and said, "What can you tell me about this? How can we shed some light on the extinction of the dinosaurs and all the other creatures at this time from this clay layer?" Luis analysed this clay layer and found something very interesting in it. What he was looking at was an element called iridium. Now, iridium is very rare on the surface of our planet. There is a lot of iridium on planet Earth, but most of it is locked in the Earth's core, so the crust is relatively impoverished. However, when Alvarez analysed the iridium that he found in that clay layer, he found something fascinating, and you can see it on this graph here. There's a sudden gigantic leap in the amount of iridium just associated with that 2-centimetre clay layer. It's even more interesting when you look at the distribution of that iridium anomaly globally. And it's not just occurring in Italy. It's not just occurring on continental areas. It's occurring everywhere you have that end Cretaceous sedimentation. We're picking up that iridium anomaly. So what's going on? Well, the only way that Alvarez could potentially explain getting that amount of iridium into the sediment at that age, at that level, all at the same time, was this. Extraterrestrial sources. We have a lot of iridium in comets and meteorites, and thus was born the impact scenario. Became very, very big news. It's an exciting prospect. A meteorite or a comet killing off the dinosaurs. It probably spawned more disaster movies than I can really think of. But it caused a lot of problems as well, because the geological community at that time was generally tending to think of processes that occurred, to quote James Burke, over a period that is dead slow to dead slow, effectively geological. So suddenly to have a theory and a hypothesis that proposes that there was an instantaneous impact and demise of the dinosaurs in the Cretaceous biosphere was something that was very difficult for geologists to accept and wrap their heads around. In addition, of course, Luis Alvarez was a physicist, and of course no geologist likes a physicist telling of his business. So there was a bit of a controversy started. So the people who weren't very fond of this hypothesis, being good scientists, of course, called for further evidence, as all scientists should do, because they claimed one clay layer and a bit of an iridium does not a hypothesis make. Fortunately for us, though, and for the hypothesis itself, the evidence was already there. Some really strange things about the end of the Cretaceous, things that we can't really explain too well until we look at them in the light of an impact hypothesis. Now, I just want to go through about 5 of those here. This is not an exhaustive list, but I just want to give you 5 examples. For example, when we look at the first sediments that were deposited after the impact event in the Tertiary, we find that the sediments that we can recover from there are heavily concentrated in the spores of ferns. Okay, what's unusual about that, you might ask? Well, it's unusual in the fact that it's not just in one area. It's not just in Gubbio. It's virtually global. So when you look at this fern response all around the world, it would appear almost that the entire planet was blanketed in ferns. It's rather unusual, you might guess. Well, what have ferns got to do anything with impact? Well, let me take you to Mount St. Helens. It might sound like a little of a roundabout route. But when we examined Mount St. Helens after the eruption, we found a sterile landscape. The eruption had effectively obliterated all life in that area of Washington. The first organisms to recolonize that area were the ferns. The ferns are very adapted to colonizing what you might call devastated landscapes. So the evidence of lots of fern spores, and therefore this fern blanket on the Earth, it's evidence of some sort of catastrophic event occurring there at the end of the Cretaceous. In addition, associated with the iridium and the clay layer is a lot of soot. A lot of soot, obviously, from the burning of organic material. Again, it's global almost in scale. There's a famous geologist who said it would almost appear that the entire world caught alight at the same time. So we have evidence of some sort of massive global forest fire going on at the end of the Cretaceous. Again, we could relate that fairly easily to some sort of mass impact event. These are things that we also find associated with the impact. These are called tektites. We find them particularly at the end of the Cretaceous associated between the areas between North and South America. Now, tektites are an impact feature. They occur when you have a meteorite or a comet exploding onto a ground surface, and effectively you melt or vaporize rock to form these natural glasses. We also have what we call microspherules forming in this way as well. And tektites and microspherules are very common at the end of the Cretaceous in those particular areas, as is this. This is shock quartz. If you go to the Nevada nuclear test sites, you'll find this in the rocks. Now, quartz is a very common constituent of many rocks, and when it is subjected to particular stresses that relate to a high detonation, high yield event, you get these patterns, these odd colours and crosshatches. It's called shock quartz, and again, it's definite evidence of a very explosive impact event. It's kind of like the microscopic scale, isn't it? These tektites and the quartz, but we also have what you could call macroscopic evidence as well. We have at the end of the Cretaceous, again, particularly between North and South America, evidence of widespread tsunami activity. Now, tsunami activity is not unusual. It occurs all the way through the geological record, and obviously recently we have tragic examples of tsunamis. However, the tsunamis that we find associated with these tsunami deposits at the end of the Cretaceous cannot be explained by normal geological processes, i.e. Earthquakes or volcanoes. They're just too large and cover too much of a wide area. In fact, they could potentially only be explained by something dropping into the ocean like a large pebble and causing an awful large splash. So what do we have in terms of evidence so far to support Alvarez? Well, we have the initial iridium and clay layer, representing perhaps the fragmentation of that initial extraterrestrial body and distributing this iridium around the surface of the planet. We have fern spores, evidence of some sort of recovery from a global catastrophe and the world being carpeted in ferns. We have the soot, those pointing towards perhaps global forest fires at the end of the Cretaceous, and tektites and shock quartz, which are indicative of large, high-yield impact events. And of course, we also have tsunami deposits, indicating that something probably impacted into an ocean. As I said earlier, this isn't an exhaustive list, but it still is fairly impressive. There's a lot of evidence there to support the possibility of impact. However, there's one thing that's missing here. If you are going to have an impact at the end of the Cretaceous, something that's large enough to remove potentially 50% of life on the planet, then you should have something that isn't on this list, and that's a big hole. There should be a crater somewhere, and for a long time that crater could not be found. Alvarez tried to explain it away in this manner. He said, well, we have evidence that there were tsunamis at this time, so possibly this thing impacted into the oceans. We know that through normal geological processes, oceanic crust is being continually recycled. It's being what we call subducted below plate margins. So perhaps if it impacted in the oceans, it has subsequently been subducted below a plate margin. It no longer exists. How convenient, the opponent said. So there was a crater and it's now been subducted below a plate margin. And that's effectively where the two camps were at that point, at loggerheads, one neither convincing the other, until we found this. Now, this is a diagrammatic representation of a core of rock that was pulled up from the Yucatan Peninsula. Now, this core of rock was recovered by an oil and gas company who were obviously looking for oil plays in the area. And as you go through this particular core, at the top of it, you have the rocks they are expecting. These are carbonate limestones. As you move down through this core of rock, though, odd things started to turn up. The rocks started to look fractured, melted, broken. And right at the bottom of the core that they recovered, the rocks were completely melted. What in fact they were drilling through was the impact crater. Unknowingly, they drilled right through the middle of it. Now, as a geologist, sometimes we have to make inferences about what is under the subsurface. But we have tools as geologists in the field of geophysics. And if you look at certain areas for their gravity anomalies, for differences in gravity, you can sometimes peek below coverings of sediment to structures that lie deeper in the Earth's crust. And that's what geophysicists did in this area and uncovered this thing. Now, this is a 180-kilometre circular structure. Those cores that I mentioned earlier come from right from the middle of it. And all the tsunami deposits, the shock quartz, the tektites, they all get thicker to this thing. This is the smoking gun. This is the Chicxulub impact crater. And this is what caused all those other features. When you analyse this particular crater, we're looking at something that entered into the Earth's atmosphere fairly shallow. It's about 20 to 30 degrees, and we're looking at an impact body that's about 10 kilometres in diameter. Now, to me, 10 kilometres in diameter doesn't really mean anything. I need an analogy to actually get that into my head. So if you want to think of an equivalent-sized body, think Mount Everest, entering into the atmosphere and impacting. Incidentally, Chicxulub is where the geophysicists base a lot of their equipment. And kind of interestingly, when you translate Chicxulub, Chicxulub translates as tail of the devil, which seems fairly appropriate in this case. So a lot of material was thrown out from this impact event, and a lot of it moved towards the northwest. So a lot of material was kind of excavated, and we find a lot of this, what we call ejecta material, around in the Yucatan area, but also a lot of it in Texas as well. Some of the ejecta material, which is composed of jumbled masses of rocks, some of those fragments get almost to house size in their size. So we're looking at a massive event here. When you're considering the amount of energy that's released in this event, we're looking at 6.2 times 10 to the 7 tons of TNT. Doesn't mean anything to me. It's just a big number with a lot of zeros after it. So again, I have to keep thinking in an analogy. So if you want an analogy for this, think of all the nuclear warheads that existed at the start of the presidency of Ronald Reagan. Then multiply them by about, say, 25 times, put them all in the Yucatan area and set them all off at once. That's the amount of energy that that number kind of represents. When you have that amount of energy released, you're not just going to fracture rock, you're not just going to melt rock, you're going to vaporize rock, turn it to gas instantly. And that's what happened in this particular event. We're pretty sure that 100 cubic kilometers of rock was turned to gas instantly in this event. So what's going to be the effects of that? Well, obviously it's going to be a fairly impressive light show. Anything that's close by to that impact event is going to be vaporized. So if you're a dinosaur there, sipping on your margarita with your sombrero on, you're going to be gone, turned to gas with the rest of the rock. As that heat pulse, though, moves out from that impact center, you're going to see the combustion of any organic material, partly explaining all those forest fires. But remember, we're also melting a lot of rock and splashing it out of the crater to form those tektites and microspherules. Those are going to re-enter into the atmosphere, heat up, and act like further little incendiary devices, further spreading that giant forest fire. And in addition, remember, we're landing into an ocean too. That explaining the massive tsunami deposits that we find at the end of the Cretaceous, that massive splash. So that would have been fairly traumatic. It would have been an incredible event, and if it was to occur today, we would see incredible devastation. However, does it explain just in its instant the death of all the dinosaurs, for example? Probably not. There are probably dinosaurs that could have survived that initial impact event. It's the longer-term effects that are the most serious and the most worrying and troubling for the biosphere. Remember, we're impacting and throwing up a lot of material into the atmosphere. I remember back in the 1980s when Mount St. Helens erupted. I was living in the United Kingdom at the time. And a number of weeks afterwards, you could find a thin patina of ash on the car windshield. It was fine material that had travelled into the atmosphere and travelled all the way to the UK. Now, Mount St. Helens is orders of magnitude tinier than the Chicxulub event. So you could imagine an awful lot of material was thrown up into the atmosphere, and it's going to hang in the atmosphere for a long time and effectively just shut off the sunlight completely. We're looking at the sunlight being shut off for maybe weeks to several months. Obviously, it's going to make the world pretty cold, but probably even more significantly, you're going to stop photosynthesis on the land, and probably even more significantly, in the oceans as well. Microplankton is going to severely be affected by this and their lack of ability to photosynthesize. So after the cold conditions, after all that material has rained out of the ocean, out of the atmosphere and formed a clay layer, which is what Alvarez was picking up, what's going to happen then? Is things going to be fine? Well, I'm afraid not really. After the cold conditions, we are going to have a turn to hot conditions. And that's because in the Yucatan area, we're vaporizing a whole bunch of rock. And a lot of that rock was actually limestone rock. It's calcium carbonate. When you vaporize calcium carbonate, you produce carbon dioxide, a well-known greenhouse gas. That probably caused maybe around 10 degrees temperature increase in global temperatures, again, further impacting the biosphere at this time. We're seeing a rapid shift now from cold conditions into hot conditions. Cold conditions for perhaps months and hot conditions perhaps for years and decades. It's difficult for the biosphere to keep up. It's not just these hot-cold conditions that are the problem, though. I'd like to focus just on one final aspect of this impact event, which would have caused a lot of stress for the biosphere. It's probably not the only one, but this is another one I'd like to bring to your attention. In any high-energy, high-yield event, such as a nuclear explosion, you can physically burn the atmosphere. By that, I mean you force the combination of nitrogen and oxygen to form oxides of nitrogen. Those nitrogen oxides then very easily combine with water vapor to form nitric acid, which then rains out of the atmosphere as acid rain, acidifying the oceans and soil profiles. It gets worse, though, because it's not just nitric acid we have to worry about. In that initial vaporization of all that rock, it wasn't just limestones that were being vaporized. There's a rock called evaporites associated with those limestones. Now, evaporites are common rocks. We find them commonly all the way through the geological record. They're forming today. Think of the Dead Sea, for example. It's a very salty body of water which is evaporating, and salt crystals are precipitating all the way around its margins. Here's Death Valley, a salt plain here. We can see that the original lake has evaporated away, and now we're just left with salts on the bottom of the ancient lake bed. It's happened on a vast scale as well. This is the Mediterranean during the Cenozoic times, and we know that the Mediterranean has at times closed off at the Straits of Gibraltar, and the entire Mediterranean basin has evaporated away, just leaving a massive salt plat. So salt formation in this way is very common. And we know that salt formation had also been going on in the Yucatan area. Now, the salts that we get in evaporites are, some of them, very familiar. Halite forms in evaporites. That's common rock salt, the salt that you use in cooking. But another common mineral that we get in evaporites is gypsum. Now, gypsum is calcium sulfate. It's very rich in sulfates. When you vaporize that, you form sulfur dioxide. That then combines with rainwater. Now we're producing sulfuric acid, more acid rain. It's important here to realize, though, that we're not talking about battery acid. You might see that in some of the more sensational programs. It's not that strong, but it's strong enough such that you're changing the pH, the acidity of the soils and of the oceans, such that you're further stressing the creatures that are trying to live in those environments. More stress for the biosphere. So what are the impact effects? Well, we would have had an initial blast, vaporization of everything that was close by, massive fires and tsunamis generated by that impact, and then perhaps cold and dark conditions by all that suspended material in the atmosphere. Following that, due to carbon dioxide and greenhouse warming, we would have had maybe warm conditions for perhaps decades. And then after that, or associated with that, I should say, acid rain effects as well, causing further environmental degradation. So really stressing the biosphere. The question is, though, could impact be the only causal factor in the KT extinction event? Well, we have a problem with that, because we know that before the KT event, before that clay layer that we talked about earlier in Gubbio in Italy, creatures were already going into extinction. So the biosphere was already looking a little dodgy. So there must be another reason why we have these particular extinction events occurring. And we think the culprit in these earlier extinction events, and probably also associated with the KT extinction event, is this thing here. This is the Deccan Traps. Now, the Deccan Traps is an area of basalt lava in India. You can see some of the layers in this photograph here. But when these were initially erupted, they covered about 1.5 million square kilometres of the Indian subcontinent. That's almost half of the area of India. Now, the basalt isn't really a problem. You can, if you're a creature, just migrate out of the way. The major problem, though, are the gases associated with that particular event, with that volcanic eruptive event, producing gases that will affect the ozone layer. They will themselves cause acid rain, but also produce an awful lot of carbon dioxide and therefore more greenhouse effects. Greenhouse effects which would be added to potentially by the Chicxulub impact. So in conclusion, when we're looking at the Cretaceous Tertiary extinction event, it would appear that the biosphere was already stressed, and the KT impact was that final nail in the coffin. It's what took the extinction probably further than it would have gone. If it wasn't for the KT impact event, we very well may still have dinosaurs on the planet today, but it was the KT that took them out of the picture. Something that's kind of sobering and interesting, though, is that in both these causal factors potentially for the KT impact, both the Deccan Traps and the KT impact event itself, carbon dioxide is one of the big villains causing global warming. Today, we're adding carbon dioxide to the atmosphere at a fairly alarming rate, and we're also losing species at what has been described as an unprecedented rate. It's been proposed, perhaps, that we might be moving into the 6th extinction event right now, making studying these past extinction events even more critical. I'd like to finish, though, on a positive spin, if you possibly can give a mass extinction event and death from the skies a positive spin, and I'd like to bring it in the form of this guy here. This is Purgatorius. Now, the reason why it's a positive spin is because extinction events free up ecological space. They clear the house and they let new creatures evolve. If it wasn't for the KT extinction event, mammals and the primates that were to follow through the mammals would probably still be scampering around the feet of the dinosaurs. It was the death of the dinosaurs that probably allowed the beautiful diversity of the mammals to evolve, and eventually human beings as well. The question I'll leave you with finally, though, is did the dinosaurs really go extinct? Well, when you look at it, no. When you consider both birds and a particular group of the dinosaurs, the theropod dinosaurs, those are the dinosaurs with 2 legs like Tyrannosaurus rex, they are indistinguishable. They effectively are the same creatures. So the KT extinction event saw the extinction not of the dinosaurs, but just the non-avian dinosaurs. So if you go out today and maybe feed the ducks on the pond, or if you go out and throw a few breadcrumbs to the pigeons, be very careful. There are dinosaurs about. Thank you.
We hope you've enjoyed this specially commissioned lecture from The Teaching Company. The Teaching Company is a unique publisher. For nearly 20 years, we've produced the great courses, college-level courses taught by only the most engaging professors that universities like Harvard, Stanford, Princeton, Vanderbilt, and Georgetown have to offer. We've created a University of the Best, designed in careful collaboration with our customers. We identify the top 1% of college professors based on teaching awards, published evaluations, newspaper write-ups, and other sources. Only those professors who score high on customer reviews of auditions are chosen for the great courses. Our courses are not merely recorded, they are crafted, designed from beginning to end with the needs of lifelong learners like you in mind. The proof of these claims is in each of our courses. Recently, an outside service surveyed 3,600 of our customers, and they rated our courses an average of 8.97 on a 10-point customer satisfaction scale, with 10 being extremely satisfied. Most publishing companies don't guarantee their work. We do. Every great course comes with our lifetime satisfaction guarantee. If a course is anything short of completely satisfying, you can return it for another course or for a full refund. No questions asked. We've done everything that the laws of physics and economics allow to make your decision to bring the great courses into your life easy and rewarding. Visit us online at www.teach12.com to browse our extensive catalog of over 250 comprehensive courses in subjects such as science, literature, history, philosophy, mathematics, fine arts, and more. Or give us a call at 1-800-TEACH12. That's 1-800-TEACH12 and speak to our knowledgeable customer care team. The only thing left is your decision. Here's the choice. Just say no to the dead time of car radio chatter or junk television, and instead embark on exciting intellectual adventures with the great courses, great learning experiences that will stay with you for the rest of your life. Thanks for your time.